All right, so y'all go ahead and do the factoring and the math knowledge question. Pause the video, and then once everyone is finished, you can unpause the video, and I'll go over the correct answers. So for this factoring, you're going to start by removing a 2. And so you're going to have x squared plus 10x plus 25. And then that in the parentheses will factor further. It'll factor as x plus 5 times x plus 5. And so we're going to have 2 times x plus 5 squared. And so that would be your answer for the factoring. For the math knowledge question, we have 20 spelling words. Which of the percentages is possible as a percent of the number of words you spelled correctly? Well, 20 out of 100, that has to be divisible by 5. So the only one of these that's going to be divisible by 5 is 85%. So B is going to be your answer. You can't get 77% of 20 words spelled correctly. Same thing with 88, 96, and 99. Okay? So we are looking at lesson 88 today. We're dealing with exponential functions. We're looking at both growth and decay. So hopefully you'll understand exponential functions after this lesson. This is the formula that you're going to use. A sub t equals A sub 0 times e to the kt. The A sub t is the amount that you have after whatever time t that they give you. So after a certain amount of time is elapsed, A sub t is your value. A sub o, or A sub 0, is the amount at time 0, the initial amount that you have. The e is just e. It's that little button on your calculator, that 2.7 number. That's what that e is. The ln is right next to that button. K is some constant that we're going to have, and you're usually going to have to find it. It's not going to give it to you. And then T is your time. Okay, so you want to make sure you know that formula and what those variables all represent. So looking at an example, the number of bacteria present at noon was 400, and 9 hours later the bacteria numbered 800. Assume exponential growth and find the number of bacteria present at noon the next day. So the first thing that you're going to have to do is solve for your K. And the way you're going to do that is to use this formula. So the initial amount was 400. And then 9 hours later, we have 800. And so now what we have to do is solve for our K. The way you're going to do that, first you want to get rid of the 400. So you're going to divide by 400, and that's going to give me 2 equals e to the 9k. Now we have an exponential equation, and so we're going to add an ln in front of both sides of our equation. We did this a couple weeks ago. Hopefully you remember that. Now we're going to move our exponent to the front, so I have 9k times the ln of e. Remember that the ln of e is just a 1, so it can go away. And now I can just divide by 9 to get my k. And my k value is the ln of 2 over 9. Now you do not want to actually plug that number in yet, because we're going to use that whole number, not just a rounded number. Otherwise your answer is going to not be very accurate at all. So assume exponential growth. We want to find the number of bacteria present at noon the next day. It measured at noon, and so at noon the next day, that is a total of 24 hours. So we're looking for the amount at 24 hours. The initial amount that we started with was still the 400, and then we have our k is ln of 2 over 9, and our time is 24. Okay? So if you plug that into your calculator, you should get 2,539.84. And so that's the number of bacteria that you would have present at noon the next day. So that's the number that you would have present at noon the next day. But now I want to show you, if I had used a rounded number. So let's say I had said 400 e to the 0.077 and then times 24. Do you see how I get a slightly different number? Instead of getting 2,539 9.8, I get 2,538.8. And so I would have to mark that wrong on your test because you didn't use the full decimal, okay? So you got to make sure that you use the whole thing. So if you don't want to have to plug in the ln of 2 over 9, like I did up here, you can do it like this. 400 e to the, this is what ln of 2 over 9 is, and then multiply that by 24. And then you still get the same number as what I got right here. Okay? So if you want to do it that way, you can. You just need to make sure that you use the whole decimal that the calculator gives you and not the rounded number. Okay? So now let's look at the next example. The number of bacteria present when the experiment began was 1,200. After 100 hours, there were 2,700 bacteria present. Assume exponential growth, find the number, or find the time required for the number to increase to 30,000, and sketch the graph. So we're going to start with our formula. We started with 1,200, and then after 100 hours, we had 2,700. So the first thing that we're going to want to do is divide by 1,200 to get our E by itself. And so 2,700 over 1,200, if you divide it out, is actually a fraction. But you can write it as a decimal. And it'd be 2.25. And we have E to the 100K. So we add an ln in front of both sides of our equation. And so I have the ln of 2.25 equals 100K times the ln of E. Remember, the ln of E is just a 1, so we can make that go away. So divide by 100, and your K is going to be the ln of 2.25 over 100. So that's your K right here. You're pretty much always going to have to find K before you can do anything else. Now it wants us to find the time when we end up with 30,000. So we started with 1,200, and then our K was the ln of 2.25 over 100, and we're solving for the T this time. So we're going to divide by 1,200. And that's going to be 25 equals E to the ln of 2.25 over 100 times T. And so now we can add an ln in front of both sides of our equation. So the ln of 25 equals the ln of 2.25 over 100t times the ln of E, which would go to 1, so that disappears. And so now we're just going to divide by the ln of 2.25 over 100. So when you plug that into your calculator, you have to be careful and make sure that when you divide, you put a parentheses around this part so that it divides by the whole thing. So do ln of 25 and close your parentheses, and then divide by parentheses ln of 2.25, close parentheses, over 100, and close those big parentheses. And so you should get, for your time, 396.94. And it was hours, because it said 100 hours, so we've got hours. So that would be your time. Now it says to sketch the curve. Now, for the curve, it's really not too bad. All I'm expecting, you've got your time and the amount at time t. And then we initially had 1,200. And we increased. And so that would be the curve that you would do. That's it, okay? Now if you decrease, you would not do this. That's not an exponential curve when you're decreasing. A decrease would look like this. So you're either going to have this one, or you're going to have this one, okay? So one of those two is going to be what your curve looks like. Looking at another example. The amount of substance initially present was 400 grams, and after 90 hours, only 380 remained. Assume exponential decrease and determine the half-life of the substance and make a sketch of the graph. Well, we're going to start with our formula. We initially had 400, and then after 90 hours, we were down to 380. So you can go ahead and divide by 400, and you should get 0.95. And so we add an ln in front of both sides of our equation. So the ln of 0.95 equals 90k times the ln of e, which is a 1. So we divide by 90, and our k is the ln of 0.95 over 90. Now we want to determine the half-life. Well, if we started with 400, half of that is 200. That's what the half-life means. When does it get down to half of what you started with? So we have 400 e to the ln of 0.95 over 90, and we're solving for the time. So divide by 400, and you'll get 0.5 e to the ln of 0.95 over 90 t. So you add an ln to both sides of your equation. So I have the ln of 0.5 equals the ln of 0.95 over 90t, and then times the ln of e, which goes away because it's just a 1. And so we're going to divide by the ln of 0.95 over 90. So again, you're going to need to put big parentheses around that whenever you plug it into your calculator. So you have ln of 0.5 divided by the ln of 0.95 over 90. And so you should get 1,216.21, and it was hours, so that's our units there. And now it says to make a sketch of the graph. So for our sketch, we have our time, we have our amount at a certain time, and we started at 400, and it's an exponential decay. So it goes down. And that's all that you have to do for the sketch. You don't need to actually put it on a graph. You can just do it on your paper like that, okay? So hopefully that helps you with exponential functions. So we've got one more example. A radioactive substance decays exponentially. After 100 years, we have 500 grams left, and after 200 years, only 300 grams remain. Find the amount of substance that was initially present and the half-life. So on this one, they don't give us what the initial amount at time 0 was. So we're going to have to just start with that after 100 years, 500 grams is left. Okay, so our initial amount that we're going to use is 500. And then we have 300 left after 200 years. It said after 100 years, 500 is left, and then after 200 years, only 300 grams remain. So the time from measuring for the 500 and the 300 is 100 years. So our time is 100 there. Okay? Because after 100 years, we had 500. So this is time 0. We have the initial amount. And then 100 years, we have 500. And then after 200 years total, we're down to 300. Okay? And it's an exponential decay. So we're going to have something that we started with as more than 500. So that's where that 100 comes from. We're not using 200 because that was from the very, very beginning time. Okay? So we divide. 300 divided by 5 is 0.6. And I have e to the 100k. So the ln of 0.6 equals 100k times the ln of e. And you divide by 100 to get your k. So that's your k value. So now we need to figure out the amount that was initially present and also the half-life. So for the amount that was initially present, we know that our k is the ln of 0.6 over 100. after 100 years, we had 500 of the substance. And that will allow us to solve for our A sub O. So the way that you're going to do that, you're going to plug this number into your calculator. Now the 100 and the 100 will actually cancel. So we really just have the E of ln of 0.6, which is just 0.6. So 500 equals A sub O times 0.6. So 100 divided by 0.6, not 100, 500 divided by 0.6 gives you 833.3 repeating. So that is the initial amount that we had. And then we also want to find the half-life. So to find the half-life, it doesn't matter what your initial amount and your final amount are. We know our E is this. We're looking for the half-life, that's a time. Pick a number, and then pick half of it. 50, half of it, is half of 100. I can pick 2 and 1. It doesn't matter. I could go ahead and make that a 1 there, and make this a 0.5. You're just picking two numbers where one is half of the other. So now we're going to add an ln to both sides. So we're going to have the ln of 0.5 equals the ln of 0.6 over 100 times t, and then times the ln of e, which goes away because it's just a 1. So we're going to divide by the ln of 0.6 over 100 to solve for your t. And so plug that into your calculator. And you should get that your time is 135.69, and it was years. So 135.69 years. That would be your half-life. So hopefully that helps you a little bit with your exponential growth and decay. You are pretty much always going to have to find your K when you're working these problems. On your homework, you do get to omit number 11 and number 12, so make sure you do those tonight so we can go over any questions you have tomorrow.